was what got me started with all of this. But it's, you know what it is? Good morning, everybody. Where are you? What? Where are folks? Oh, I know what I'm sorry. I've been working. I never see. I can monitor the number of people who are online. So we forgot to let you guys come on in. So we'll just chat until you guys come in. I apologize to you guys for 2022. And then we'll usually put it here. Yeah. In case people don't have it. But anyway, it's kind of interesting. You know, what I'm doing here, just so you guys know about the streaming part, right? This stuff is going to be implemented in the LACCD district. But they call it HighFlex. So they're doing a trial version of all of this that you see here, like at Pierce College. But there was training this week on HighFlex. I didn't go to it because I've been too busy doing this other stuff, right? But they're essentially doing what I'm doing. So they're going to try to do this, which is great, you know, but they have to buy whatever this HighFlex equipment is to do. But this was all done, in all honesty, because I've had students in like 125 who, during the pandemic, the school's trying to, last spring, I guess they're trying to get everybody to come back, right? And they said, you know, we don't want, you know, some of them said, we already had COVID. We don't want to come back. They're scared of coming back. I said, well, don't worry. I'll do this streaming. I'll stream from the classroom then. So you guys can stay home, still take the class, stream from the classroom, and you guys will still be, it'll be okay, you know. Some of them said, I like the streaming because there's videos I could go back to for the lecture and it was helpful. And one student said to me, she said, you know, I would have failed if I was face-to-face. I said, why would you have failed? You know, what are you talking about? And she said, she told me was, you know, because sometimes there's some students that have trouble taking notes. You know, they have real trouble taking notes, and then going back was really helpful for her. And she ended up getting an A in intermediate algebra and an A in statistics. She did the both just because of that. So it has worked for some people, you know, it's worked. So I'm grateful for that, you know, but it's a pain in the butt. You guys know, as you can see, you got to bring it and take it down. It's easier from home, leave it there. But if there were people who benefited from it, then good. And, you know, for winter, I'll let you guys know this. You know, they're trying to get everybody to come back, right? So I did this whole thing in winter. And during winter, I had about 8 students who came down with COVID. But the good news is they were at home. They weren't on campus. Do you guys see what I'm saying? So it kept us here safer. You know, so that was the whole idea. So it worked. So, you know, I talked to the president about that, and they're aware of these things, but things are political. So they got HighFlex, whatever that is, HighFlex. They're working on HighFlex. But okay, I'll stick with what I'm doing, I guess. I don't know. What do you guys think? Is it useful, you think, in some ways, or is it not useful? I don't know. Is it useful? Is it really? Oh, that's great then. That's good to know. So, in other words, I'm glad the nightmare for me is worth is worth doing, because that is actually the most important part. You know, if it wasn't, then, and I would go, oh, okay, I don't know. But anyway, yeah, a lot going on in case you guys didn't know. And Wednesday, I'm trying to gather a lot of statistics students to speak at this trustee event, trying to educate our trustees about the issues, and hopefully they're going to be receptive. But politicians, you know, yeah, whatever. Hey, John, thank you. See, this is a student from my class yesterday. Tell me good luck for what we're doing. He's a good guy, John. Anyway, I'll get you guys your test back today. You know, I was talking to a few students earlier. You know, it wasn't a perfect test for me personally because when I usually gauge tests when I do them after. And when I do a test, I'm like, you know, I want to feel good about a test. I was like, yeah, it was kind of an okay test. I don't know. That was just my feeling. Some of the questions were like, oh, that was pretty straightforward, pretty simple. Some were not, so it was a mixture. You know, some you're like, okay, that one took some work. So I don't know. Maybe I'll give you guys an extra credit assignment here. You know, because like I said, I do feel like it's not worth a lot of points. Some points, you know. 20, 25 points, you know. I'll think of an extra credit assignment here to kind of consolidate what we've been doing because the idea is that when you go to Calculus 3, you know how to do Calculus 2. And in Calculus 2, you got to know how to, in Calculus 3, the biggest complaint from instructors are, they'll say, and it's a big issue, I'll be talking about it really in a department meeting, it gets discussed. Students in Calculus 3, you want students to be able to integrate and know how to differentiate. Because now you're going to do it with multivariables, 2 variables, 3 variables. So right now we're only focusing on 1 variable, a single variable, you know. But, you know, don't look at it like, I think personally, Calculus 2 is the course that had the most work, in my opinion, by far. Calculus 1 is a shocker. It's new. Calculus 2, you're like, oh my God, it's an extension, a lot of work. As you guys can see, oh, I got to do partial fraction decomposition. Oh my God, the trig integrals, you know, got to remember trigonometry, and there's a lot of work there, you know, and especially if you haven't taken a course in that stuff, you know, then it's by far like, oh my God. And like I said, I was a kid in that situation myself because as a student, my trig instructor was crazy. He lost his marbles. He would come up, even though we're in the dark, he'd turn off the lights, you know, and we're all like, why are the lights off? And he would just sit there for an hour reading the book, trying to figure out what to do. And that was my trig experience. So I understand what it's like to have to skip a course and then now have to catch up. I understand that intimately. And that was the worst course to skip because your science courses are based on trigonometry. So I had to go back and learn it on my own, read it, and it was a difficult task that I've always remembered. Like, geez, and I teach trig now, you know. So it was a blessing and a curse. The blessing was that was how you had to learn how to really be a student, you know. It was a curse because it was like an uphill battle, but you know, but that's the name of the game, I guess, you know. So fighting uphill all the time. Anyway, all right, we do got enough students here. Sorry I didn't send you that announcement, but good morning. Good morning to Shusi. Good morning to Paula. Lely, good morning. Nguyen, good morning. Oscar, hey Oscar, good morning. And Luke, good morning. Luke is here. Okay. Well, let's stop all the yakking and let's get to work because there's a lot of work. As you guys know in Calculus 2, it's work. But you know, I think it's a very foundational and pivotal course. So let's get to work and you know this foundation. Where are we at? Improper integrals. So I'm going to give you guys this worksheet here. Okay, it's on my website on statistics transition here because I wrote this for the calculus class during the pandemic. And as you guys can see here, improper integrals, I'm going to tell you what they are. You're looking at really what's known as a proper integral, right? So this is the integral from a to b from some continuous function. F has to be continuous. By the second fundamental theorem of calculus, you got to have a continuous function, okay? So what's going to happen now is this. That function f, we're going to see some integrals that we can integrate when it's not continuous. And you're like, are you kidding me? Yep. So this integral f is not going to be continuous, and we're going to learn how to integrate. That's really known as a type 2 integral, but we have a type 1 improper integral where we have what's called infinite intervals. And so maybe I think it's just best for us to start to write down definitions here, right? So here's what I'm going to say. Today we're going to focus on, here's what you guys already know. They're really called proper integrals in this context. And you know, okay, already that's the antiderivative evaluated at x is a and x is b, okay? This function f is nice and continuous. Now, okay, how is this going to change for us? Well, I'm going to call this type 1. This is the first type we'll focus on today, type 1, where you have what's known as infinite intervals. And that's when you integrate over, that's called an infinite interval. It's not from a to b. It's not going to be from a to what? Yeah, a to infinity. Or minus infinity up to what? B. See this? Okay, or over the whole real number line. You go, what do you mean, what's the real number line? Negative infinity to positive infinity. So we're going to have some intimate intervals. That's our first type today. Okay, so what we'll do then, you say, what are we going to do? We're going to take, I'll give you guys an example. We'll start off with an example. And my first example is going to be from 0 to infinity, and I'll have x over x squared plus 2 dx. And I think we're going to square this here. Yeah. Okay, so I want to point this out. This is a type 1 improper integral because it has an infinite interval. Right? And you're really integrating over the interval from 0 to positive infinity. Okay? That's what they call that, an infinite interval. It involves infinity. So in order to do that, you have to use a definition. So we're going to have to define this, right? So here's the definition for this improper integral from 0 to infinity. Is it f of, yeah, I think we're going to use f of x dx. Let me double check my worksheet. Yeah, okay. All right. Okay, so by definition, this is what this equals. You're going to introduce a dummy variable, right? You're going to say, now, this is going to be the limit from 0 to now t f of x dx. So this is thought of as what's called a dummy variable. It's kind of a word that just doesn't even make sense. It's just called, you can even just call it you change the variables if you want to call it that, right? And then you're going to say now, this is going to go as t goes to infinity, okay? So this is really done in 2 steps here, okay, in all honesty. That's the definition you're going to actually use. 2 steps. Where is that? All right, you guys okay with that? And so if I go back to my website, you're going to see a little bit of detail. Okay, I guess that's the first, that's called case 1. All right, so it's called case 1. Now, let's go through how this really works, okay? So we can see all the language. So there's 2 things you're going to have to do. First, you're going to have to, this is the integration part. You're going to have to integrate. And that's what you have to do first. Okay? And then the second thing you do after you integrate, you apply the limit. So it's essentially two things. Integrate, then limit. And that's it. Okay, so that's your definition. So if you know how to integrate, that's the first part. If you know how to take a limit, then that's the second part. So we'll see how to do that together, right? So, okay, you guys okay with that? How we start this off? So now what you can do is just write down the definition. This is the limit. As t goes to infinity, we're going to integrate from 0 to t, okay, x over x squared plus 2 squared. And then that's going to be dx, okay? So this is what I'm saying. We got to integrate first. It's going to be from 0 to t now. So as you can see this here, what do you think? You say, well, how do I integrate? What technique would you use? U sub, right? You guys okay with that? You're going to have to use what? U sub. So down here, this is your u. You say, what is u? U is x squared plus what? 2. Okay, you guys okay with that? And then if u is x, that's going to be du dx is going to be 2x. And then you say, what does that mean? That means dx is du over what? 2x. Okay, so let's go through the integration. X, u squared. This would now be what? du2x. Cancel the x, and you get what? 1/2 integral. I'm going to put u to the minus 2 du, right? Okay, you guys okay with that one? You guys see that there? So now when you integrate, this is 1/2. U to the minus 1 over minus 1, that's going to be minus 1/2. It's minus 1 over 2u, right? But remember, this integral is not in terms of u, it's in terms of x. So we say, what is that u again? It's going to be x squared plus 2. Okay. So this is the part in gray, but we have to evaluate that. I want you guys to focus on this. What are your limits now? 0 to what? T. Okay, you guys okay with that? 0 to t. So this is going to be now what? 0 to t here, right? It's the same limits now. So there it is. That's the key. That's what you're going to have to integrate. That's the first part. So now you might say, well, what does that equal? Remember, this is going to be f of t minus f of what? F of 0. Okay? So that'll be here minus 1 over 2. Not x squared. Now going to be what? T squared, right? T squared plus t minus a minus 1 over 2, 0 squared plus 2. T0. So apply that limit. So notice what you end up with. You end up with 1/4 minus 1 over 2 t squared plus 2. Okay, so this is the part that I'm talking about. This is the part that's in what? That's the gray part. We're right here. Let's see. This is f of what? T minus, you got that here. F of t minus f of 0. So they're both already negative, right? Yeah, they're both already negative. Yeah, that's something. You know what I would give you guys as advice, because I remember as a student I used to get, it's tricky, right? When you have a negative antiderivative, you go, oh my God, that's a negative, right? So what I used to do is I used to do it exactly as I show you guys here, parentheses, parentheses, and I always had to pay attention here because it was always like, oh, you got to be careful, you know, got to be careful with that. So, and then, like I said, we kind of like starting this off to be positive, like a 1/4, right? So that's the first part. So in other words, using this definition, that's what you do first. Now, this is the second part. You apply the what? The limit now. The limit as t goes to infinity. So everything now here, and this is sometimes called, they call that f of t, right? Because it's a function of t. Well, you already had that f of t, but let's change that here. I'm sorry. They call that, I'll call this portion at times, not f of t, but integral. It's a function of t, right? I of t. So you now really take the limit now as t goes to infinity of that integral in terms of the variable t, and limit t goes to infinity, 1/4 minus 1/2 t squared plus 2. Okay, you guys okay with that? Now again, properties of limits. What are properties of limits? Limit of a difference is different to limits. Limit of a constant is a constant. So this is really 1/4 minus the limit now. T goes to infinity, 1/2 t squared plus 2. And do you guys know what happens to this limit? Where does this limit go to? That limit goes to what? That limit goes to 0, right? So what's your final answer? It's 1/4. Okay, so the answer here is going to be 1/4. Now, here's what I want to remark. What does this mean? Okay, right? What does this actually mean here? Okay, you guys okay with that? What this means, I'm going to draw a picture for you guys. If you were to sketch this curve, and we can see what the sketch is. Here's the x-axis. Here's the y-axis. Essentially, here's kind of what's going to happen for these answers, right? If we're going to integrate from 0 to infinity, you know what we're talking about? Area under the curve. 0 to infinity. So here's our interval, right? What that means is the area under that curve is really what? 1/4. It's finite. I guess we can't see that. Your area is finite. It's 1/4. Because isn't that what an integral does? You guys see what I'm saying? So what you're doing here is you found out that this here is a finite answer. Finite just means number. That's all. Okay? And so when you have this answer here, and I'm going to describe this to you guys. This is the language we use. We say the improper integral converges. Okay? Because it's a limit, and a limit converges or a limit diverges, right? So we have that kind of language. So this is your first kind of situation. If you find that it's finite, what do you guys say about the limit? The limit what? Converges. So that way it converges to what we call a finite number. It is. It is, because what you did here, in all honesty, is you started the process this way, right? Here's what the process really is, if you want to draw this picture. This here in red, that's the I of t I just described to you guys. Or we can even call it A of t, area in terms of t. But you took that limit t and you went to what? Infinity. I'm sorry, let me take that back. We got this is bad. Take that back. Here's what I mean. You integrated from 0 to t. This portion is I of t, right? Because you went from 0 now to some variable t. And then you took that limit t to infinity, and what we're saying is that's a finite limit. So yeah, you can actually integrate over an infinite interval and get a finite number. And that is insane. And that blows your mind. You go, really? A finite number? That's one situation. You're only going to have two situations. You're going to have that it converges to a finite number, or you're going to have this other situation called divergence. And it's kind of simple in a way. Let me express this to you guys here, fundamentally what this means. Okay? Fundamentally, this is what this means here. You can have an increasing function, and if I said to you, what's the area under that curve over the infinite interval? Well, this is a situation that we say diverges, because now that I of t goes to infinity, where up here, your I of t went to that 1/4, a finite number. Okay? But you can have a situation where if you had an increasing function like that, guess what's really going to happen? If you try to integrate from 0 to infinity, this is not going to be what? Infinite. This is going to be what we say a divergent situation. The improper integral diverges. Okay, because remember, what's going on really when you integrate? Remember these approximating rectangles? Even though you have infinitely many of them, the height gets bigger, bigger, and bigger. So those areas get bigger, bigger, and bigger. So it blows up in the sense it gets so big that the area is not finite anymore. It's infinite. You know, and then in all honesty, you can have a decreasing. This is a decreasing function. It really comes down to, does the function decrease fast enough so it increases? Now that's an advanced calculus idea. So you can have decreasing functions that actually diverge as well. Area goes to infinity. It's just because that the curve doesn't get to the x-axis fast enough. You say, what do you mean fast enough? Because of these approximating rectangles, right? That height gets bigger, bigger, and bigger. It explodes. Easy to see here, but when you see it here for a decreasing function, you might say, what just happened? Well, it just meant that curve didn't get to the x-axis fast enough. And you'll see that. So if we actually look at this in Desmos, right? I like looking at these functions in Desmos just to kind of express to you guys to see that here. That y equals here. What does y equal? X divided by, in parentheses, x squared plus 2, and then come out of there, raise it to the second power. And so as you guys can see here, yes, from 0 to infinity, that's a decreasing function, right? Gets close to the x-axis, so those approximating rectangles get smaller, smaller, and smaller, so that the area gets smaller, smaller, and smaller. The height gets smaller. Remember, your width is always the same, delta x, but the height is going to change. And so, yeah, okay, you can suspect that it can converge, and it's actually getting close to the x-axis fast enough, so yeah, it'll be a finite area under there. And it is crazy because it's like you're going from 0 to infinity. Yeah, absolutely. So ladies and gentlemen, that's kind of like I said, it's a simple concept in some ways, but it's really two steps: integration and then followed by a limit. So you got two ideas, and that's using just this definition. Well, it's really about finding area, right? Finding this area, but this portion needs to get close. Needs to do what? It needs to get close to the x-axis really quick in order for the area to be finite. If it doesn't, it's going to be too big. It'll be infinite. It really, yes, it depends on how fast that curve gets to the x-axis. Exactly. But, we don't compute that in this class. Like we don't compute it. Like there's called a rate of convert, how fast does it get to the x-axis? That's like in an advanced calculus setting. So, it's like sometimes when people say, okay, I'm learning this mathematics, where do I extend it? Well, it gets extended when you start to take other classes. Other classes may be in science, other classes may be in math. And then they'll build on it, so you're always building on your foundation here. And like I said, in a very simple way, you're finding area under a curve. It's either going to be finite, meaning it's a number, or it's going to be infinite, meaning it's just too big. It would be positive infinite. It would just really be too big. It could be negative infinity if the area is under the x-axis, because it's negative, right? Those rectangles the heights are negative. And that's what you're looking at for these first types. That's it, area under the curve. And that's right what I'm talking about. If you get close to that x-axis fast enough, whatever that is, it's going to be finite. That's all. But it's just a two-step process. And I give you, there's three types of this, or three cases, right? So if I go back to my what? Yeah, this is going to be definition, how we say this thing converges, right? And then there's notation for convergence, by the way. This is the notation that we just talked about. When you converge, if I can put it here, symbolically, all you do, this is the same way of saying convergence. You're saying the area is smaller than that infinity, right? That's just saying convergence. How do we say divergence symbolically? This is just symbolically. You're saying that area equals infinity. And we'll see an example of that. There's a very famous example of this. I can even make it up right now really quick. I can say to you, here's a good example. 0 to infinity. I can take the x squared curve. Right? What do you guys know about that curve? That's your quadratic. That's going to go up forever. Is that right? So if we try to look at this very simple idea, use your definition, limit as t goes to infinity, change the variable now from 0 to t, and that'll be x squared dx using our definition. Yes, we have to do what? Integrate here first. We're going to pay attention to that integral. We know that's 1/3 x to the third power 0 to t, 1/3 t cubed minus 1/3 0 cubed, which is 1/3 t to the third. Now remember, I call this I of t, and we want to take the limit of that. Right? So you say, okay, there's your first part. You got the limit. So now you can say, okay, the limit t goes to infinity of 1/3 t to the third power. What does that limit become? Do you guys know what that limit is? It's infinity. Yeah, this is saying that the area there is just too big to be finite. Those approximating rectangles explode. I shouldn't say explode. They just the area gets too big. And that should make some sense, because you say, why does that make sense? How does that x squared curve look? Yeah, it's a parabola, opens up, right? If maybe Desmos can draw a better parabola than me. But weird. Y equals what? All right. And I hate it when it's in red. Anyway, those approximating rectangles from that interval 0 to infinity, they get bigger, 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 and bigger. They increase without bound. So you got a problem. Area is just too big. Too big to be finite. That's all. So this is your first type of improper integrals. This is to me, this is fascinating. You know, I just like, my God, I mean, I don't know. There it is right there. And then to express to you guys a question like this is what I mean by, you know, I have this example in my notes. You know, you might say, could they give me something like this? Yes. X squared plus 3x plus 2 dx. Okay. Now, I want to just kind of briefly remark, you see this function? That function is continuous over the interval. So this is continuous. It's an important detail. Over 0 to infinity. So for these integrals, at least for the first part when you get started, they're all going to be continuous over that infinite interval. Okay? Generally speaking, when you get started. Now, more complicated questions eventually, I don't think we do that in this class, but you might have discontinuities there, and there's we'll deal with the discontinuities next time. You know, you see how you handle discontinuities next time. Right now, it's just infinite intervals, but it's continuous functions over that infinite interval. So you say, okay, limit t goes to infinity, 0 to t, 1 over x squared plus 3x plus 2 dx. And I'm going to be consistent here. We're going to stick with this what? Gray and then gold. So as you guys know here, right, you might say, what do I have to do to integrate this integral? Right? What do you guys know what you do here? What do you have to use? Partial fraction what? Decomposition. You go, oh my God. Yeah, that's what I mean, right? So what I mean is you build up on this. So this is at the end of the chapter, which requires you to know about integration, right? So PFD. So, you know, you can go with, you guys know how you start that, right? You're going to factor this, which is x plus 2 times x plus 1. So I'm going to express to you what that really becomes, because I've done all the PFD stuff, but this integral here, and I think I might even have on my website. Let me go back to my website. Let me go double check here for you guys. All right. Memory serves. This is improper integration. If you guys want to see some more videos of these cases, see what I mean? Case 1, case 2, case 3, case 4. Case 4. Oh no, this is improper. Sorry. Wrong place. Those are the integration by partial fraction decomposition. And maybe you guys can't see it. Scroll out. Improper integrals. Infinite intervals, case 1. Infinite intervals, case 2 and 3. What did I do? Oh, what is? Oh, that's weird. I got to fix that. What did I do? Something's done that wrong there. All right, I'll fix that for you guys. What is this? Why is that in? Let's see. What? That's crazy. All right, I'm going to have to fix this. Note to self. Put the proper links. That's weird. But I have examples here. I'm going through these examples. So if you want to see all the detail, it's right there. You guys know what I mean? Here's the A, B. Here's the partial fraction decomposition. So you guys can see some of those examples there. And I'll get the videos up. That's weird. I got to remember why I did that. Okay? So I just want to kind of let you guys know it's going to be there too. Anyway. So when I go straight to this, I'm going to tell you what that answer was. It's the natural log absolute value x plus 1 over x plus 2, and that's going to be evaluated from 0 to t. So this is my I of t I'm talking about. Okay, so remember, or you could call that f of t, whatever. No, it's not I of t. I apologize. This is your f of t. So you want f of t, well, f of x, and you're going to get f of t minus f of 0, right? What's that? Oh, I'm sorry. Oh, you're right. Thank you so much. Okay. There we go. So here's the gray portion. And if you want to see the detail, it's there in the example portion, right? There's the integral. And so when you evaluate the limits now, it's going to be what? Natural log absolute value t plus 1, t plus 2. Natural log absolute value 0 plus 1, 0 plus 2. Okay? So this is going to be and you know they're not going to put they can put absolute value 1/2, but that's going to be what really natural log 1/2. Okay, so that's the I of t. Now what do you do with the I of t here? You're going to take the limit now of this as t goes to infinity. Okay, so you're going to take, this is now the limit here, so you guys can see up there. See there. So this question now is going to be limit t goes to infinity, natural log t plus 1, t plus 2, minus natural log of 1/2, and I guess you put a bracket, but this is really, all right, you know, I don't like to write it all again, but I'll write it all again. Remember, minus, it's the limit of a constant. I guess I'll write it. Limit t goes to infinity, natural log 1/2. This limit we know is what? Natural log 1/2, because that's a constant. Okay, that part's a constant. So the question is going to be, what is this limit? Okay, now I'm going to remark and give you a little detail. Got to get this coffee going. You might say, how am I going to evaluate this limit? Right? You guys know something about as t is going to infinity. You know what that kind of means? T is what? Positive, right? It's going to infinity. Now, what that really means here is this portion, I can just say, it's not an absolute value. It's going to be now what? Parentheses. T is positive. Just like I can take this natural log here, I can say 1/2 is positive, so it's really going to be parentheses, right? Absolute value 1/2 is just 1/2. Anyway, so we have to see what this limit goes. So we're trying to say, as t gets big, remember these limits? We want to know, where does t plus 1 over t plus 2 go to? That's just like saying, what's this limit? This is a Calculus 1 question. Do you guys know what I mean? So this is now a Calculus 1 limit question. So in Calculus 1, what did you guys do? See that t? What do you guys do with that? Yeah, divide everything by t. So it's like a Calculus 1 question now. Say, okay, limit t goes to infinity, 1 plus 1 over t, 1 plus 2 over t. So this limit is actually just going to be 1. So what we found was that this limit goes to 1 here. Now, that's an important detail. You're not done, because what do they want to know? What does the natural log go to? So you can now say, oh, the natural log of all of that, t plus 1 over t plus 2. What does this go to? You guys know? It goes to the natural log of 1. Is that true? You guys know what I'm saying? It goes to, because natural log is a nice continuous function. That goes to the natural log of 1. Let's move everything over here. And what's the natural log of 1? Do you guys know what this is? Natural log of 1 is what? 0. So in other words, this limit goes to what? 0. Yeah. So you say, okay, what's the final answer then? You go, okay, then that's going to be minus natural log of 1/2, or if you don't like negative signs, that's a natural log of 2. If you don't like negative signs, that's a natural log of 2. So ladies and gentlemen, you go, well, natural log of 2, it's a natural log of 2. That's a finite number. Okay, this is finite. So this is, again, a convergent situation. Finite, so symbolically, we can go back to this original integral, and you say, you know what that means? This is finite. Well, let's first of all say that the area under that curve equals natural log of 2. This is really what they're saying. This integral converges to a finite number. So as you guys can see, that's a pretty good what? Pretty good definition. It's not always convergent. Anyway, but you have to know how to do some what? Integration. Is that right? Now, let me give you guys another situation. It's kind of an exotic situation. I want to talk about it. Okay, so this is going to be the integral of cosine squared. So this is going to be the limit. T goes to infinity, integral. So to t, cosine squared theta d theta. Right, so do you guys remember how to integrate cosine squared? You got to use the right identity. Remember the right identity? This portion here, 1/2, 1 plus cosine 2 theta. Yeah. Right, so again, sometimes you can say, okay, I'm trying to find the integral, right, or area. 0 to t, 1/2 plus 1/2 cosine of what? 2 theta d theta. I'm going to distribute the 1/2 now, which gives you 1/2 theta, right? Now let's see, derivative of sine is cosine, so that's going to be plus 1/4 sine 2 theta. Double check, because the coffee's not in me, ladies and gentlemen. And what does that give us? You guys know what that gives us? We're just going to have to do it all. 1/2 t plus 1/4 sine 2t minus, if you want to see that, 1/2 times 0 plus 1/4 sine 2 times 0. This portion here is 0. That's the integral portion. Okay, now the limit portion, because you go, oh, we got to do a limit, right? So you got to take that limit now. So this is going to be the limit here. T goes to infinity. Okay. I want to share with you guys what this means here, because you're going to say, what is going on here? All right. So let's take a look at this as properties of limits. So you have the limit, t goes to infinity, 1/2 t, plus the limit, t goes to infinity, sine 2t. So you guys know, where does this limit go to? Right? Doesn't that get big forever? 1/2 t? T is getting big, so okay, 1/2 of t is still getting big. So that limit's infinity. But let's talk about this limit. And I've got to find a color. I don't know what color. Green. All right, let's talk about that part, right? What happens here with this? This is going to be... This is probably something... This is what I'm going to say is an exotic situation. I'm trying to remember if we did this ever in this class or in the Calculus 1. I'm trying to remember. Maybe not. Maybe this is the first time you guys see this here. When you're taking a limit at infinity for sine, you guys know what's going on? What's going on with the sine functions? There's no sine 2t. This is periodic, right? Like if I showed you in Desmos, because this is an interesting exotic situation. You want to know about it because it sometimes pops up. You know, not all the time, but I'll just say sine 2x. This is what I mean, right? Sine is periodic, right? It goes on forever. You can go, what do you mean as the variable x or t gets big forever? What happens as this goes on forever, right? Well, here's your problem. Sine is periodic and sine oscillates between +1 and -1. So when this pops up, when this shows up, this function here oscillates forever between what? Plus and minus 1. What that really means is that it does not converge. I'm going to say, therefore, it does not what? Converge. What does not converging really mean? It what? It diverges, right? And what does this mean? This is the essence of diverging. We call that limits going to infinity it's just the opposite of convergent is diverging. So what I want to kind of conclude here is this. You can say, what is that infinity plus what? Well, you can make arguments that, well, it doesn't matter. Infinity plus or minus infinity plus a finite number, infinity minus a finite number is still infinity. It's not converging. It goes to oscillates between positive and negative. So, make a long story short, they're going to ask you to show if this converges or diverges. You can say this equals what? Infinity, or put the phrase divergence. So this is a very special type of divergence. You know, this is more direct from divergence, from our definition. This is a more indirect concept, but they throw it out there at you. You know, it's a very common thing. What happens is sine as, forever. You know, if you say, what's sine of theta as theta goes to infinity? Sine of x as x goes to infinity. It oscillates forever between plus or minus 1. It's a form of divergence. Yes. Cosine as well, yeah. It'll be the same for cosine. Absolutely. It's a type of divergence, we call that, because it oscillates forever. Like, the question is, what if this limit was for cosine? Same answer. Well, tangent's periodic. It doesn't oscillate, right? If you look at the curve for a tangent curve, so you'd have, you could conclude, well, let's see, we look at tangent. We have to look at the details of the function, but this is something they kind of throw at you. It's kind of interesting. And then here's another good example. I love all this stuff. I don't know about you guys. I just like, geez, if you spend all that time learning how to integrate, you should be rewarded with something interesting, right? You spend all that time looking at integration, you go, geez, So here's another idea. And I was just thinking of this argument for this trustee right now, in all honesty. Unbelievable. What do you guys know about that function and this interval? Right? It doesn't have to be from 0 to infinity. It can be 1 to infinity. See this interval here? You guys know about the natural, you know about this 1 over x function? Yeah, we're going to integrate it, right? But here's what I want to point out, right? This is called the ellipse. This function, the 1 over x, I want to emphasize, that's continuous over the interval. You guys know what I remember? So it's nice and continuous over the interval from 1 to infinity. Right? So if you said, hey, I want to we're trying to find this area here. Now, this goes back to some of the remarks I started the day with, right? If you were to look at this curve, what might you say? Because I've had students do this on a test. They say, you know what, Mr. Judge, that's a decreasing function over the interval. If I try to integrate from 1 to infinity, you know what they'll say? They'll say, less than infinity. What does that mean? They conclude convergence. Right? Remember the approximating rectangle argument? Rectangles get smaller, smaller, and smaller. Those areas get smaller, smaller, and smaller. So they conclude, converges, I don't even have to do the work. Well, let me show you guys something. That's not the case. Okay, let's go through the details. Right? So what's the definition? It's the limit t goes to infinity. We replace that infinity with t. Introduce the dummy variable. And then you say, okay, here's my integral portion. I want to take, that's the natural log absolute value of x, evaluated from 1 to t. Absolute value of t minus natural log absolute value of 1. You guys know this portion is 0. Well, t is going to be positive, so that's another way of saying just natural log of t, right? Okay, you guys with me on that part? So here's my I of t. This is the integral. I now have to apply the limit now, right? So then that's the limit now as t goes to infinity, natural log t. Where does this go? Right? Remember the natural log curve? Notice this, ladies and gentlemen. This is why I give you guys curves every calculus student should. No, they call them, used to call them calculus students should know. I call them B-STEM. See this here? What is this limit? This is the natural log curve. What's the limit? Infinity. Okay, you guys see what I mean? See what I kind of went through? Just look at the curve, natural log. So what does that mean? This actually what? diverges. This area, this diverges. Say divergence. So it goes back to the remark I was trying to make to you guys. The essence of convergence and divergence with these first type of integrals is simply this. Does the curve get to the x-axis fast enough? In this case, the answer is no. Fast enough for the area to be what? Finite. So the answer is no. So sometimes students will go, oh, I'm just going to kind of look at that curve. It's a nice simple curve. I can deduce this. You can only deduce it if you can only do that if it's actually an increasing function. It's not guaranteed if it's decreasing. Do you guys know what I'm saying? It's not a guarantee if it's a decreasing function. It is a guarantee if it's an increasing function. Interesting idea. You know, I don't know about you guys. So this area is like, wow, I'm going to say that area is infinite? Yes. I don't know. What do you guys think? Is that pretty good? I don't know about you guys. And then let's use the second definition. Let me give you guys another example. All these examples are there. Integral. Now you might say, what is negative infinity to 0 of a function? X e to the x dx. It's another great example of this. And so you got a function again. This function, this is nice and continuous. Now look at the interval they gave you. All right, so, okay. Let's see, what is the browser here? Let's go back to the browser. I don't want to look at that part. Where's our notes? Okay. We call this here what? Case 2. Okay, now what's the real difference? It's just that the lower limit now is negative infinity. That's the only difference. Okay, instead of having the upper limit being positive infinity, the lower limit is negative infinity. That's all. That's all it is. So we're integrating over this. This is the lower limit now. So the definition is the same. Let me double check here. I don't want to, because sometimes I use a different. Yeah, you're going to use t still, right? I'm going to show you what I'm talking about. So in other words, you're going to replace this with a what? Let's give you the definition. That's a little weird. Something's bothering me. What's bothering me? Yeah, I think it's, okay. It's a weird thing. Why did I change the letter? What's bothering me? A to B. Okay, whatever. Negative infinity to B. All right. Limit now. This is all you do. See this here? See that? You can just replace that with t. That's all. Okay, you guys with me on that? And so you go, oh, replace that with t. Yes, and this stays the same. There you go. And there's your t. So what that means for us here then, if you said, well, how do I integrate this? You're going to say, oh, that's going to be the limit. T goes to minus infinity. T to 0. X e to the x dx. There you go. I of t. Okay, so how do you guys integrate this? What do you guys use? Yeah, use ibuprofen, right? IBP. Integration by parts. And to share with you guys what you get by integration by parts, it's in my notes there. X e to the x minus e to the x for IBP, integral from 0 to t. So now apply the limits, 0, e to the 0, minus e to the 0. Remember, put your parentheses and then minus t, e to the t, minus e to the t. Okay, you can see notes there or see examples. So notice what this gives you. This portion 0. This is 1. So this is going to be negative 1 minus t e to the t plus e to the t. Okay, you guys okay with that? And that's my I of t, I guess, if you want to call that. This is the I of t. Integral in terms of t. So now you want to apply the limit, but the limit doesn't go to positive infinity. That limit goes to negative infinity. Okay? Okay, you guys with me on that one now? Now, use properties of limits. You say, what are my properties? Limit of sum of limits, limit of a constant, blah, 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 right? So by properties, I guess we'll have to write it all down. Limit t goes to minus infinity, negative 1, minus that limit, t goes to minus infinity, t, e to the t, limit, t goes to minus infinity, e to the t. Okay, you guys okay with that? What's the limit of a constant? Not a constant? What's the limit over here? You go, oh my God, e to the t, but t goes to minus infinity. Yeah, that's a 0. Good. Good. What do you guys think? So The real issue is, so far, you're going to say, okay, what's the real issue? What's this limit? You guys remember that limit? What's this going to be? Negative infinity times 0. Is that right? So you might say, wait a minute. Minus infinity times 0. What is this? L'Hopital's rule. Remember that stuff? You're going to have to fix this. Exactly. So remember, this is an indeterminate product. So you're going to have to fix this. You want to write this as an indeterminate what? Quotient. Is that right? So you can put, like, for example, maybe t over 1 over e to the t. Is that right? Remember the fix? And then what is this? And then if you did that, you guys know what, if you did that, what you're going to get here is, well, here's what I would think I want to do. What is that? Isn't that t over what? E to the minus t? So what's that going to be? This is going to be minus infinity over infinity. Because that's a decay. That's a, remember this curve, e to the minus t right here. That's a decay curve. What happens as t goes to minus infinity? Isn't that infinity? You guys see what I'm saying? So this is an indeterminate now quotient. Now we can apply L'Hopital's rule. So by L'Hopital's rule, we can say, oh, okay, we take that limit, right? That's the limit of the derivative. 1 over minus e to the minus what? T, is that right? Okay. Now, you might say, what is this going to be then? Well, this whole thing is the limit, and I guess t is going to minus infinity, right? T is going to minus infinity. So that's going to be a negative, really, e to the t now, which is minus that limit, t goes to minus infinity, e to the t. So let me get rid of this e to the minus t curve. Let's replace it with the e to the t curve. Okay, what is this going to be? Isn't this going to be what? Where's t going? Minus infinity for the e to the t? What do you think that is? Anybody know what that's going to give you? That's 0, is that right? So in other words, this portion is 0. That means it's negative 1 times 0, which is 0. So that whole portion is really 0. And then you say, well, what's my answer anyway? Negative 1. So yeah, so if you guys can notice here, you may see all the tools we studied, like L'Hopital's rule. You may see ibuprofen, IBP. You may see integration by partial fraction decomposition. So this is negative 1. So ladies and gentlemen, here's what we can say. If I can move this out of the way, what's this going to be? It's negative 1. In other words, it's finite, or it converges, right? You put less than infinity. So can you ever have area that's negative? Yes. What does that mean about the area? It's below the x-axis, that's all. So if we go to Desmos and you go, what's this interval? This is from negative infinity up to 0. X e to the x, right? So if we go to Desmos and we say, what does that function look like? Where is that function? Where are functions? Oh, I guess I have to scroll. Geez, there's so many things about this Desmos that I just never even knew. What is that? It's in green. Okay, you see this function? This is from negative infinity to 0. So what do you guys notice now? It's below the x-axis. But now that curve, as you're going to negative infinity, right? Isn't that curve trying to get close to the x-axis? Those approximating rectangles that we draw. So it's getting close to the x-axis. So anyway, it gets close to the x-axis fast enough such that the area is negative. It's finite. A negative number is also finite. Any number is finite. What do you guys think? I don't know about you. This is a pretty good deal. Let's give you guys another example before we take a break, right? I don't know. You guys having fun with this stuff? I know I am. I don't know about you guys. It's a break from all the madness I have to deal with. You know what I was thinking as I'm doing all this, because I multitask? Hate to say it. You know, we had a trustee who mentioned something last night, and I'm thinking of, writing the trustee, letting the trustee know, that if you're like a SLAM major, like let's say you're political science, social science, or I don't know, language arts, right? The question is, do you need algebra? What do you guys think? I'll give you guys my view. Huh? Huh? Well, yeah, I mean, he's thinking you should change all that, right? So here's kind of my response to that. First of all, he doesn't know that the pathway for some of those students, we have what's called a pre-stats. They take a pre-stats. That's like not much algebra there. It's like arithmetic and stuff. A little bit of algebra, but not much. And then you take stats, I guess. So in other words, what he doesn't know is you're not asking some of those students to take algebra anyway. Because he made a comment. He says, I haven't used algebra since I left college. But I use probability and I use statistics. Okay. Here's my response. First of all, well, if you're a SLAM student, you don't have to go that route. If you're a STEM student, you have to go that route. So let's not discard STEM students. But moreover, here's what I would say to somebody who is maybe a SLAM student and says, I don't need algebra. I think this is an important thing, right? You guys are living, and I've said this to you before, you guys are living in an age where technology is what? King. You can actually become a billionaire if you write code for some things. I mean, you guys know what I mean? This is the age that you guys are in. You're just limited by your imagination. So if you have the right skills, who knows what you can develop? You might develop something nobody's ever thought about, right? I mean, isn't there a lot of apps out there that you guys see that people make a lot of money with? There's tons of apps. What do you think you need to know if you're going to start to write some of those apps? Algebra. So it's not like you can be an old geezer like myself or even some of the trustees, right? Because you don't understand that kids today, if they can have some of those skills, they can actually become even billionaires, or you don't have to be a billionaire, maybe a millionaire. I don't know. I know of people who have written programs that have made a lot of money. They don't have to work anymore. And how did they make their money? Programming. They did some programs. And I don't think you want to shut the door on anybody, whether they're a STEM student or a SLAM student. So those SLAM students should consider maybe programming, developing apps so they too can be what? Have that opportunity. I don't know. That's just how I think. They could disagree with me all day long, but they're not in the classroom. You guys know what I mean? That's politician talk. I don't know. What do you guys think? Am I imagining things? Am I the crazy one, or are they crazy? Does it make any sense to you guys, or does it make no sense? I don't know. Guess you got to point to examples of people who've made a lot of money doing that stuff. But yeah, I mean, I've known some people who it's like amazing. I mean, I was envious of them. Like, man, why didn't I do that stuff? What the hell am I doing? If I had real time, I mean, I'd take programming courses and I do exactly what I'm advising you guys to do. You know what I mean? I've even looked into it. So I'm gonna take some I gotta brush up on my programming skills. What are the new languages that are being used? What can I use and do that? Because people who can do that, they can do very well. It's an open area for people. They don't realize it, you know. So any kind of app. Apps are ruling the world. Actually, my brother wrote some apps. He didn't make a lot of money, but he's kind of weird. You know, he wrote some stuff that's kind of, I got to look up his apps again. What are you doing, app? Oh, I can't tell you guys. He's a weird guy. I can't tell you the apps he did. He's a weird guy, but he wrote some apps. They're even sold in the Apple App Store. I don't know if they're still doing it. It was like 10 years ago. I have a younger brother who did that. But they were kind of odd, I got to admit. You know what kind of apps he wrote? Weird apps. Yeah, one of my brothers. What did he write? He wanted to log places I've gone to the bathroom. I mean, like Taco Bell at this, you know, in this city, like you could map where you've gone to the bathroom. Weird. When I worked for Amazon delivery, they give out packages, and it was barely time to use the bathroom. So I was trying to actually create an app where you could find bathrooms around you. There you go. See what I mean? See what I'm saying? Yeah, I think so. I was like, he's probably using his imagination and what was available for tools that are already there. And then he's doing this weird stuff like places I've gone to the bathroom and how you could log it all and do that stuff. I remember this years ago, and I'm like, man, what are you doing with that? It's like weird. And he did another one too. I was like, what are you doing, man? Places I've done other things, you know. Logged it, you got an app for that, right? It's like, man, what are you doing? But maybe there's, like I said, it's like you're whatever your imagination is. And you guys, as being young, I hate to say it. I'm glad to say it. You guys have pretty vivid imaginations. It's when you get old, you lose it. You lose your imagination because you get jaded. But when you're young, you're kind of open with what you can imagine. You know what I mean? It is, but it's kind of like, too, if you guys know, like in the math field, people who have won like these incredible awards in math, they generally do it when they're young. Yeah. It's like a young man's game, you know. Not all, but, you know, it's kind of interesting. Yeah, but it is kind of different. I kind of think of it as, well, I mean, it depends on the person because, you know, you guys know the phrase of trying to keep yourself young. I would say to you, there's something to it. There's definitely something to it. One of the reasons why I like being here and doing what I do is I get to be around students. Because then it keeps me what? Young and informed. Keeps me young. If I wasn't around students, I don't know what I'd be doing. You know what I mean? I don't know where my head would be because then I wouldn't be. I learn just as much from students as they learn from me. You know, I learn a lot from students. And that's why I'd rather be around students than any of these other guys all the time. Because then you're right. It is depressing because you start to realize like how you can go from somebody who's really open-minded with a great imagination of what can be done and how to do it to you get to an age where all that's gone, you know. And that's an interesting thing. That's very, very fascinating. Yeah, I don't know. That's kind of how I see it, but whew, yeah, that's pretty heavy. Yeah. Yeah, places I've gone to the bathroom. So for Amazon, did that help? Yeah, that's pretty good. Yeah, did you make any money from it? Yeah. Well, I don't think he made. I don't think my brother made any much money from it because I looked how many downloads, like 15. You know, I was like, oh my god. But you know, I know of another guy. I don't know exactly what he did. Because I got into photography, you know, and I used to be a part of this meetup group in photography. And I used to go to this guy's house. He had a couple of mansions, but they weren't big mansions, but they were big houses. You know, they weren't like huge mansions, but they're mansions, I guess. Just really, really big, nice houses. I had a couple of them. He didn't really work. And I remember it's like, well, what are you doing? Well, I do some programming. I made some programs. I did this. You know, so we made a little money, enough to buy a couple of mansions and work minimal. Maintain his whatever program it is. I just thought it was amazing. Like, man, what that was great. You know, just kind of thought made me really think about everything. Like, wow, oh, come up with a great hit program. You know, you look at all these people that come up with those great programs, and they did a lot of wonderful things. So that was just something I think that, you know, I'd say to somebody who said, hey, I never found algebra very useful. It's like, well, you may want to think again. You know, you may want to think again, but you might be, you know, if you're talking to somebody who's a lot older, maybe they've already lost it, you know. They don't realize. But yeah, that's interesting. Let's take a look at this one. Use the definition. Replace this with a T. So I heard Amazon, they actually started to unionize. So how was that, though? Yeah. I hate to, you know, if you say, hey, what's going on with the stuff I'm talking about fighting back against, it is those corporations that are behind it, you know, that are trying to make a profit on people and remove opportunity for them to go to school, to get them into the for-profits. And yeah, my younger brother got into he went to school that way and he regrets it. Yeah. All right, let's look at this integral. Oh, I guess it's a nice U sub, right? So that one's a nice U sub. Anyway, so let's U sub. You guys know the deal. Let's write down what that becomes, right? You're going to get minus 1/2 e to the minus 2x, evaluated from t to -1. All right, so be careful. I would say f of -1 minus f of t. Okay, because I might have to, sometimes I might write that down or write all this stuff down, especially when you start having a bunch of negatives everywhere. It can be very confusing, so, So I'll write down the format like that way. It kind of helps me. And minus 1/2 e squared plus 1/2 e to the minus 2t. Anyway, okay, I guess we have to take the limit now. Let's get the right highlighter. Now, limit of sum of limits, right? And then you have a limit of a constant. So what do you guys have here? Minus what? 1/2 e squared. So I'm going to use all the properties. I get to pull out my constant here. So I'm going to move everything. And so let's be careful here, right? We want to be careful. I'm gonna express to you, this is a limit as t goes to minus infinity, and that's a decay curve, right? E to a minus power. So we say we have growth, we have decay. Anybody know where that goes? What's that going to be? If it's helpful to you, I suggest you do it. I would do it. I would draw a decay curve. And then I go, oh, okay. But t is going to minus infinity. This is what we mean, right? Going to minus infinity, right? So where is this going to? That goes to what? Infinity, is that right? Excuse me. And so the question is going to become this. Let's think about this. Minus 1/2 e squared plus 1/2 infinity is still what? This whole thing is still infinity, right? Or it's still infinity. So what do you think that means? Infinity minus, if you want to change the order, you can. It doesn't really change the answer. So infinity minus a finite number. You guys know how I think about it? Something arbitrarily big minus a finite number. It's kind of like saying, you got Oprah money or Bill Gates money and somebody took away 50 cents. Does it change anything? No. So the final answer is really what? Infinity. That means divergence. So infinity plus a finite number or infinity minus a finite number is still going to be infinity. Doesn't change the situation. It's arbitrarily large still. So this is a divergent situation. So you go, oh, okay, this is infinity. There you go. And e to the minus 2x, if we said, what does Desmos say about that, right? It's a decay curve. So I don't think we have to look at that. It's decay. Yeah. Anyway, we'll E. Where's E if we can find it? Okay, I guess it might need parentheses. Yeah. So if you're going from like -1 to infinity, right? Isn't that like negative infinity to -1? Right? Isn't that all to the left? Of course the area under the curve is what? Infinity. Do you guys see the point? Yeah, because of course it is. Anyway. All right, let's take a nice break. That's amazing. Good stuff. Take a break. All right. You guys can get some coffee or I don't know. Whatever you like. All right. Okay, ladies and gentlemen, let's take a look here. We got the final case to consider, case 3 of the infinite intervals, really definition 3. Okay. Let me take a few seconds here. 5:57:40. Okay. All right, ladies and gentlemen, I apologize for taking your time there, but I got to get this email out, and it's interesting. Okay. So, ladies and gentlemen, here's the third case. Now, you might say, what's the third case? That's when you integrate over the whole real number line a function. Okay? So you might say, okay, here we go. It is still assumed that this function here is continuous. F is continuous. But now notice this is over what? Negative infinity to positive infinity. This is over the whole real number line. Now this situation is interesting as well. You can have convergence, you can have divergence. So you have to look at some various examples. So here we go. This is infinity to minus infinity. Now I want you guys to consider the following. Note. Just notate from what you know from Calculus 1 and integration that all you got to do is take this integral and break it up into two integrals. Okay? In other words, we can integrate from these two. Okay, so in other words, and this is for any C. For any C, you know, in the interval, and it's going to be because it's a real number, right? For any value on the real number line. So typically 0 is a nice number to use because remember when you integrate, you like zeros, right? Because zeros make a lot of answers go away. So I typically use 0 when it's available. But generally speaking, you could use any number. You could use 1, -1. You could use 1/2. You can use 20. You can use pi. You can use e. I like 0 personally. Okay? So that's all you really do. So in other words, what you do is you create two improper integrals. Here's your first one. Here's your what? Second one. So you create two what? Improper integrals. Two. Okay, now I'm looking at my list of examples here, and it's kind of like I don't know if it's the best example to use because it's a little bit, you'll see what I'm talking about. And I could look at the book and see if they have any others, but you might look at this one and you go, oh my God, what in the world does this mean, right? Let me write it a bit nicer. So to kind of remark for you guys here, the following. You see this absolute value? What does that absolute value mean? Do you guys know what that means? This here is a piecewise function, right? So I'm going to say you got the absolute value of
I didn't get
x.
that. Could you try again?
Uh-oh. What was that? Oh, what does that mean?
I didn't get that.
Oh,
Could you
Siri?
try again?
Sorry, Siri. We didn't see. That's creepy. We didn't do anything to call Siri, did we? Oh my God, is that what I said? I don't even know. See how I need students? I need students in my life because they know what's going on. I don't. Interesting. So let me show you guys this absolute value. Let me show you really how you handle this piece right in here, I guess. I don't know what colors to use anymore. And in fact, I'm really showing you what this minus absolute value is, in all honesty. But it starts with this portion right here. Okay, so I'm going to say, always remember when you have a piecewise, absolute values is a piecewise. So that means this is when x is greater than or equal to 0. And it's opposite when x is what? Less than 0. Okay? And then you might say, then what does the opposite of x mean? And let me find I guess we use blue. What does this piecewise function mean? It means it's minus x when x is greater than or equal to 0, and it's minus a minus x when x is less than 0. Okay? So my point is you got a nice piecewise function where you have this first piece for positive numbers, and you have this first piece for what? Negative numbers. All right, you guys okay with that? Now, what's opposite an opposite? You say that's just x. All right, you guys okay with that? So you're going to use these two pieces. Use minus x and use x for those pieces. Now you might say, well, what does that give you? Let's move this out of the way. Right, so you have from negative infinity, I'm going to use up to 0. You say, why is 0 good? Well, you see this portion, you see the zeros? So for minus infinity up to 0, which one are you going to use? Orange or are you going to use green? Green, good. So that's going to be e to the what? X dx. Plus, now from 0 to infinity, which one are you going to use? E to the what? Minus x dx. Okay, so let me color coordinate this so everybody can see the details. So in other words, I have two integrals now to perform, right? And I need convergence for both in order for it to converge. They both have to be finite because a finite plus a finite is finite. But if I got a finite plus infinity, infinity, right? You guys see what I'm saying? So in order to have convergence, I'm going to put that note. For convergence, we need both integrals to converge. And I'm going to be very specific, improper. Because integrals don't converge, but improper integrals do converge, okay? All right. Okay, so in other words, let's kind of do this one. Let's do this first one here. Okay, so, all right, well, I don't know. Let's do this green one, I guess. Copy. This is a limit as t goes to what? Negative infinity from t to what? 0? E to the x dx, right? So then you say, what happens here? Well, isn't that e to the x from t to 0, e to the 0 minus e to the t, so it's 1 minus e to the t. And this is that integral. So we apply the limit now. 1 minus the limit, t goes to what? Minus infinity, e to the t. This is a growth curve, but you're going to minus infinity. Anybody know what that means? What is this limit going to be? You guys know what that limit is? Is that limit 0? That limit 0. So in other words, this first integral converges. Okay, so this integral here in green is 1. So I'm going to put a big 1 here. Maybe that value is 1. You guys with me? 1 plus a number. Now the orange integral. Limit t goes to infinity, integral 0 to t e to the minus x dx. Okay, let's look at both of these here. So this is going to be, if we integrate, u sub, right? Minus e to the minus x from 0 to t. So minus e to the minus t minus a minus e to the minus 0 minus e to the minus t plus minus the minus e to 0 is 1. So I can write it this way, 1 minus e to the minus t. Here it is. So you can take that limit as t goes to infinity. One minus the limit t goes to infinity e to the minus t. So this is a decay curve, right? E to the minus t. What happens with decay as t goes to infinity? Goes to 0. Good job. Good job. That goes to 0. And so this limit also is what? This limit also equals 1. So we're going to say, okay, you're also 1. All right. Pretty good. So don't forget, what do you do here? This is a sum because we're adding, we're using this principle. So this is really convergence for both. You need convergence for both. If you don't have convergence for both, you can't say convergence because it's a finite plus a finite. Finite numbers plus finite numbers is finite. If you get divergence for one, it's going to diverge. So my final answer here is going to be, what's 1 plus 1? Yeah, it's a nice question. This is 2, ladies and gentlemen. And that's your final answer. So in some ways, let me copy this all. Okay, you can say, here's your conclusion. This equals 2. And 2, by the way, is what? Finite. Okay, you can also write it this way. Right, putting smaller than infinity just means convergence. Anyway. So I kind of want to look at that in Desmos. What is this exponential function? Where do you have the absolute value? Absolute value function. That's weird. Maybe we'll just put, oh, there we go. Absolute value. Oops. So let me show you guys what this function looks like. You guys see this function? All right, what do you guys think? Area over the whole real number line. See how as you go to positive infinity, that curve gets close to the x-axis? See how you go to negative infinity, the curve gets close to the x-axis? So you go, oh my God, that's a pretty good thing. Exactly. So let me actually give you another example just to kind of illustrate a point, because I know if I don't show it, you know, I'm going to say, what do you think would happen if we asked you to integrate over the real number line? Something very simple, like e to the x. I mean, this is a very simple example, but it proves a point. Okay? Right? So remember, what do you want to do with this? Since this is over the whole real number line, this is continuous, a nice continuous function still, right? Split it up. What's our favorite split? My favorite is 0. Right? Just to kind of give you an easy breezy. I don't know, what do I tell the intermediate algebra students? They say, easy peasy. Right? First integral. Second integral. Yes, this is a sum. So what do you do? What do you do here? Limit t goes to minus infinity. And from t to 0. E to the x dx. Okay. So focus on the integral again, right in here, and then focus on the limit after that, right? So we get e to the x from t to 0. E to the 0 minus e to the t. 1 minus e to the t. So now apply the limit. So it's going to be 1 minus the limit. T goes to minus infinity, e to the t. So isn't this, what kind of curve is this? Is that a growth curve? Okay. So for the growth curve, for the left portion, this is convergence. This is 1, right? Or no. T goes to minus infinity, right? This is going to be 0 again, right? So you say, okay, that first one is 1. Okay, what about the next one? Limit. T goes to infinity. Integral. E to the x. 0 to t. Focus on this. E to the x, 0 to t, e to the t minus e to the 0, e to the t minus 1. Now you're going to take the limit, right? Limit. T goes to infinity. E to the t minus 1. So what do you guys know by properties of limits? Limit. T goes to infinity. E to the t minus, limit of 1 is 1. What is this e to the t limit as t goes to infinity? Do you guys know what this one is? This one is what? That's infinity. Infinity minus 1 is still what? Infinity. You okay with that? All right, so now here's what I'm going to say. This is going to be what again? This is infinity. So if I said to you, 1 plus infinity, I think of Bill Gates and Oprah money. If you gave Oprah $1, is that going to make a difference? The answer is no. It's still going to be what? Infinity. You guys know what it says? So if you add any finite number to infinity, it's still going to be infinity. If you subtract any finite number from infinity, it's still going to be infinity. Because that's the idea of infinity. It's arbitrarily large. It's so large we can't even assign a numerical value to it. And that kind of should blow your mind too, because it's not like a billion or a gazillion. It's like, it's even massively bigger. It's infinite. It's like never ending in terms of money. Imagine if you had never ending money. You could never get rid of the money you have no matter what you did. That's crazy. So here's the story. If you see divergence for one integral, if we started this off and we got divergence, you know what I would say to you? Don't even bother doing the second one. Because it wouldn't matter. Do you guys see what I'm saying? You guys see my point? If I started with the green integral, I would say stop right there. As soon as we see an infinity, stop. This thing diverges. Okay? Because if you get divergence for at least for one integral, any one, then it's going to diverge in this last case. Doesn't matter what the other one is. And that's kind of like my advice. So I wanted to kind of get that, and I was hoping I would hit it with infinity first and say stop right there, and that leaves an impression on people. You go, oh, I don't have to continue? Nope, you don't have to. And you say, oh, great. And, but yeah, that's kind of what we're going with. Anyway, ladies and gentlemen, what do you guys think about this stuff? Is that pretty interesting? Right, you guys notice it's based on first one thing. You got to know how to integrate. And then after that, you have to remember how to take limits. And sometimes you do have L'Hopital's rule, you know. But the next, what comes up next is we're going to have still what's called finite intervals. So if you go, oh, I'm going to see what comes next. You know, what comes next is you're going to have finite intervals now, right? So we're going to say, oh, you got, but the function f is discontinuous over the interval. You go, well, how do I handle that if my function is discontinuous over the interval? Well, I'll show you. It's another improper integral. It's going to be a very similar approach. It's going to have these definitions that you see here. We have case 1, case 2, and then case 3. We have a whole other 3 cases. If I was here on whatever Monday, we would have finished this whole thing, you know. So if you guys want to look that over, you can. If you want to get started on that too, I'll put homework in the assignment portion on this. Maybe I should do it now if I can. Right, let me take a look at the book. And this is going to be improper integral. Oh, wait a minute. This is homework 3 now. Sorry. Oh, we got to pass back that test for you guys. Yeah, here's what I'll do. I'll give you homework on this. It's called homework now what? 3. And so stay tuned for that. I'll put that in there. It's going to be improper integrals. What chapter is that? 8.8 or 8.7? I think it might be 8 what? 8.7? No, it's 8.8. 8.8. So I'll give you guys some questions on 8.8. Improper integrals. And I'll pass back the test for those who are here. Okay, so I'll put that there for you guys in a bit. So if you are at home, print your name for attendance purposes, and we'll see you guys later.